ABCD constant of a three-phase transmission lines are given. The sending end voltage is 400 kilovolt. The receiving end voltage under low load condition is, right. So we are given the ABCD parameters, and what else is given? The sending end voltage is given to be 400 kilovolt, and also it is given that it is no load condition. So when there is no load, it means that the receiving current is going to be 0, right. So these are the given values. What do we need to find? We need to find the receiving end voltage VR. First and foremost, whenever you are solving a power systems problem, you need to understand that the voltage that will be given will be the line voltage. See, here nothing is mentioned, and when nothing is mentioned, it means that it is a line voltage. Okay, so this is by default. So here this is a sending end voltage. If it is 400 kilovolt, it means that it is the line voltage. So what is the expression? Vs is equal to AVR plus VIR. We need to find VR. So VR is equal to Vs by A, because IR is given as 0. Okay. So this is equal to 400 divided by A is given as 0.8. So 0.8. We are only concerned with the magnitude. So this will come out to be 500 kilovolt. So because they have not mentioned specifically the line or phase voltage, we are finding the line voltage. But if they are asking the phase voltage, right, then you can either take Vs, you can take the phase voltage, or if you are taking this as the line voltage, then the final answer you have to divide by √3 so as to get the phase voltage. Okay, so just be careful with this line and phase voltages. A 10 km long lossless transmission line has a reactance of 0.3 ohm per kilometer and negligible shunt capacitance. Find the ABCD parameters, right. So it is given that it is a 10 km long line. Okay, so just because long is here, don't think that it is a long line. So they just mean the length of the line is 10 kilometers. Okay, so when it is 10 kilometers, what does it mean? It is a short line because it is less than 100. So we are dealing with a short line here. So what will be the representation for a short line? Resistance, inductance, and this is the sending end current, voltage, receiving end current and voltage. Okay, now you can either use the direct, we have already derived the ABCD parameters, so you can use that directly. What are the ABCD parameters? This is 1, Z, 0 and 1. Otherwise, you can consider it like a two-port network and you can find out the ABCD parameters. You can go either way. Okay. Now what else is given in the question? It is given that it is a lossless transmission line, right? It is lossless, meaning there is no resistance. The resistance is 0 because it is lossless. And here you have reactance, this is given as 0.3 ohm per kilometer, right? Then what will be the total reactance of line? This is going to be 0.3 into the line length, which is 10. So this is 3 ohms. Okay, so because reactance has only imaginary part, we have J3. So what will be Z? R plus J into X. This is equal to simply J3, right? So you can get the ABCD parameters as 1, J3, 0 and 1. Okay, so this is the answer. A 100 km long transmission line is loaded at 110 kilovolt. If the loss of the line is 15 megawatt and the load is 150 megavolt ampere, the resistance of the line is. Now here it is a 100 km line, so it should be a short line. What other information is given? It is loaded at 110 kilovolt. Okay. So whenever they say loaded, it means that the voltage at the point where we connect the load. So that is the receiving end voltage, right? So the receiving end voltage is given as 110 kilovolt, and like I told before, unless until mentioned, it is going to be a line voltage. So here, since they have not mentioned, we are going to consider it as line voltage. What else is given? The line loss is given as 15 megawatt, and the load is 150 megavolt ampere. So when the unit is volt ampere, then it means it is the complex power. Okay. So the receiving end complex power is given as 150 megavolt ampere. Okay. Now we have to find out what? We have to find out the resistance of the line. Now how can you find the resistance? Resistance is associated with the line losses, right? So here loss is given. I square into R gives the losses. That means you need to find out the current, the receiving end current. Okay. Now how can you find the receiving end current? Here you have the complex power and the voltage. So first we will find out the current, the receiving end current. So how can you find it out? The complex power is given by root 3 VR into IR. So we can find out IR is equal to SR by root 3 VR. So this is going to be 150 into 10 to the power 6 because it is given in mega, root 3 into 110 into 10 to the power 3. You are going to get 787.3 amperes. Now we will find the resistance. So one more thing that you should remember here is, in the three-phase power systems, unless until mentioned, usually we take the star configuration is by default. Okay. So if there is a star configuration, that is why whenever we want to find out the phase voltage, we take it to be line voltage divided by root 3. Okay. So what will happen to the current? The line current is equal to the phase current. Okay. So the phase voltage will be equal to VL by root 3 and the phase current will be equal to the line current. Okay. So this relation is important to be able to write down the expression for power loss, right? So power loss, what will this be? The phase current, which is IR square into R, this is per phase, into 3 will give you the total 3-phase power loss. Okay. So this means that PL is given. How much is it? It is given as 15 megawatts. So 15 into 10 to the power 6 is going to be equal to 3 into 787.3 whole square into R. So here you will get R is equal to 8.06 ohms. This is what the per phase resistance. A 50 Hz 3-phase transmission line is 200 kilometers long. It has a total series impedance of 35 plus J140 ohms and shunt admittance of 930 into 10 to the power minus 6 angle 90 degrees. It delivers 40 megawatts power at 220 kilovolt with 0.9 power factor lagging. Find the magnitude of the sending end voltage. Okay. So you have to use the nominal pi model of the line. So it is already anyways given that it is 200 kilometers length. So it should be a medium length line. Okay. So we can use either the T model or the pi model, but because in the question they have mentioned pi model, we will go ahead with the pi model. Okay. Now first we will write down what is the information that is given. First one is length of the line is given to be 200 kilometers, and next the series impedance, this is given as 35 plus J140. Next you have the shunt admittance 930 into 10 to the power minus 6, and the receiving end power, this is given as active power, this is given as 40 megawatts. And what is the receiving end voltage? This is 220 kilovolt. So once again this is the line voltage. and finally the power factor is given 0.9. Okay, this is cos phi r, the receiving end side power factor. Okay, so we have to now find what is the sending end voltage. First we will draw the pi model. Okay, so in the pi model you have the impedance, the series parameters will be as it is, but the admittance we are going to divide at the two ends, right? So this is Vs, sending end voltage, sending end current. Here you have y by 2, this is z and this is y by 2. What is the voltage here? The receiving end voltage, and the current that is coming out is the receiving end current. Now if you have to find out Vs, it will be equal to Vr plus the drop across this. So we know Vr, we need to find out the current through this, we know the impedance. So if you have to find the current through this, then you need this current IR and the current through this. Okay, so we will find out whatever is required. This current through the impedance, the series impedance, we will take as I. Okay, now one more thing that you need to remember here is the model when we draw, this is for each phase, right? So the first step that you should do is you have to take the phase values. See, whenever voltage is given, it is the line value, right? So we have to first find out what is the phase value. So VR line is given as 220 kilovolt. So from here you will find out the phase voltage as 220 by root 3. So this is going to be 127.02 kilovolt. Now these are AC quantities, right? So we need the phase as well. What we will do, we will take, like always, we will take the receiving end side as the reference. So VR bar per phase is going to be 127.02 angle 0 degrees. This is in kilovolt. Okay. Next we can find this charging current at the receiving end side. So what will this be? ICR bar, this is going to be equal to the voltage across it, VR bar, into the admittance, right? You can write divided by impedance or multiplied by admittance. So here we have admittance, so we will take multiplication with the admittance. So this is going to be 127.02 angle 0 degrees into y is given as 930 into 10 to the power minus 6. Here angle 90 degrees is important, right? Phase is important. So 930 into 10 to the power minus 6 angle 90 degrees. And we should not forget the by 2 here. Okay. So this, if you calculate, you're going to get 59.064 angle 90 degrees. This is the amperes. Next what we want the receiving end current IR bar. Now here, unlike the charging current, you're not dealing with the impedance. Instead, what is the information that you have? You have the receiving end power as well as the power factor. So the power is what it is? Root 3 VL IL cos phi, the line values, right? So here you can write down PR is equal to root 3 VR line voltage, IR line current is same as phase current, so not big difference here, cos phi r. Okay, so IR is going to be the magnitude of the receiving end current. This is going to be PR, which is given as 40 megawatts. So 40 into 10 to the power 6 divided by root 3 into, remember to take the line voltage here. So the line voltage is 220 into 10 cube kilovolt, right, into 0.9. Cos phi is 0.9. So this you are going to get 116.636 amperes. Okay. Now this is a lagging load. It is given that it is a power factor is lagging. Okay. So that means the current will lag the voltage by an angle which is equal to cos inverse 0.9. Angle IR is equal to angle of VR minus the power factor angle, cos inverse 0.9. So this is going to be 0 minus cos inverse 0.9, you will get 25.842 degrees. Okay. So from here you can get the current phasor is equal to, magnitude is 116.636, angle minus 25.842 degrees. This is in amperes. Okay. So now we can find out the current through the impedance. I is equal to ICR plus IR by KCL, right? So I is equal to IR bar plus IC R bar. So this is equal to 116.636 angle minus 25.842 plus 59.064 angle 90 degrees. This is ICR. Okay. So this, if you calculate the final value, you're going to get 105.3 angle 4.48 degrees. This is the amperes. Okay. Now finally you can write the sending end voltage Vs bar is equal to VR bar plus I bar into Z. Okay. So this is going to be 127.02 into 10 cube. So we have to find for per phase, right? Then you can, after you get the per phase, then you can get the line voltage. So 127.02 into 10 cube, angle 0 degrees plus 105.3 angle 4.48 degrees into 35 plus J 140. Okay. So this, if you simplify, you're going to get 130.4 angle 6.6 degrees kilovolt. Okay. So what is delta here? 6.6 degrees. Okay. Now this is the phase. So we will find out the line voltage. This is equal to root 3 into 130.4. Okay. So this is going to be 225.87 kilovolt. A 275 kilovolt 3-phase 50 Hz 400 kilometers lossless line has the following parameters. X is equal to 0.05 ohm per kilometer, Y is equal to 3.0 microsiemens per kilometer. The receiving end voltage on open circuit will be. What load at the receiving end will result in a flat voltage profile on the line? So here this is a long line, right? 400 kilometers is given, so it is a long line. Now we want to find out the receiving end voltage on open circuit. That means when IR is equal to 0. So what will be VR then? Vs by A, and Vs is given as 275 kilovolt. Now we need to find out A. So for a long line, what is the ABCD parameters? This we have derived as cos h gamma L, Zc sin h gamma L, 1 by Zc sin h gamma L and cos h gamma L. So what is A? It is equal to cos h gamma L. Now gamma is root over Z into Y, right? So root over R plus J omega L, or you can write Jx into G plus Jy. Okay, so here we know X, we know Y, and it is given that it is a lossless line. So R and G are going to be 0. This is 0, this is going to be 0. So you are going to get J, you can take out common, into root over X is given as 0.05 and Y is given as 3 microsiemens. So 3 into 10 to the power minus 6. This you will get as J 3.87 into 10 to the power minus 4. Then what is gamma L? This is equal to J 3.87 into 10 to the power minus 4 into the line length in kilometers. Why? Because this is given in per kilometer. So this you are going to get J 0.154. Okay. Now cos h gamma L is equal to cos h J 0.154. So this is equal to e to the power J 0.154 plus e to the power minus J 0.154 divided by 2, right? So you are going to be left out with cos 0.154, but this is in radians. So you can either select the radians option in the calculator and find out this value, or if you want in degrees, if you're more comfortable in degrees, you can convert into degrees by this conversion factor. Thus you're going to get 0.988. Okay. So from here you can find out the receiving end line voltage. This is equal to Vs by A. Okay. Because IR is 0. So Vs is given as 275 kilovolt, and this is in line, that's why we will get the answer in line, divided by 0.988. So this you are going to get 278.34 kilovolt. Now what is the next question that we have here? What load at the receiving end will result in a flat voltage profile? Okay, so flat voltage profile will occur when the loading is equal to the surge impedance loading. What happens at surge impedance? The reactive power is going to be 0. Okay, at surge impedance loading, the reactive power that is generated will be equal to the reactive power consumed. Okay, making the net reactive power 0. And when this is the case, this will result in a flat voltage profile. That means voltage at all points along the transmission line will be equal. So here in this question we just have to find out what is the surge impedance loading. Okay, at that loading we will get a flat voltage profile. So this is what it is equal to root over Z by Y. So this is given as J.05 divided by 3 into 10 to the power minus 6 J. Okay, so you are going to get 129 ohms.